So what we would like to do is, given a network model, we can generate the network from that model, or we could do the other way around. So given a model, we generate the network from that model, or we can take the network and try to find the model that best fits this network. So what is the best model that will correspond to this network and is able to generate this network? So given a set of nodes, define the model for generating the network. The way we're going to do this is this model has a set of parameters that we're going to use to estimate or detect communities in the network. So, for example, if we know the friends that are part of the community and their memberships, how many communities they belong to, then we can generate the edges of the network. So these are, let's say, the nodes, and if we know the communities they belong to, we can generate the edges and link them together to obtain the structure of the network. So the first thing that we have here is the nodes. So we have the nodes and the communities that they belong to. And each community has some, and so we also have the memberships, which community each node is a member of. So for example, the blue nodes are members of the community A. The green nodes are members of the community B, and the red nodes are members of both of them, so they overlap. Another thing we have here is some parameter. So parameter for community A, piece of A, and parameter for community B, or piece of B. And that is a probability for that community. So, starting, given a set of nodes and their memberships and their communities, so the nodes, vertices, the communities, and the membership, whether they're members of those communities, and some probability for them, for that community. This is going to be the model, and given that model, we want to generate the graph. And this model is called the AffiliationGraphModel. So how does this model generate the network? How do we create the edges? If both belong to the same community, let's say they both play soccer and go to the same university, what is the likelihood that a pair of nodes belongs to the same community? So what is the likelihood that two nodes will connect if they belong to the same community? that is the parameter that we have shown up here. So each community had a parameter. So that is the likelihood that two nodes will connect if they belong to this particular community. So for each pair of nodes that belong to the same community, we'll connect them, and the probability for that will be equal to PA. So A is the community A. And so using this formula, we can compute the overall edge probability for two nodes by taking the product of all the probabilities so the probability for all the communities that they belong to. So this formula that you're seeing here shows the probability that two nodes, which are U and V, will connect or create an edge. So this formula is going to tell us whether we should place an edge between two nodes. So what this is one minus a product of all the probabilities that of communities that they do not belong to. So taking one minus that gives us the probability of the communities that they belong to. And so the reason we're doing this is because product, when we're multiplying these numbers, if they're less than 1, and if we keep multiplying them, this number will get small. And 1 minus smaller number will give us a bigger number. We can think of this as an OR function. If at least one community connects them, then we will create the edge. So this is basically telling us, giving us the formula of that will tell us whether we should place an edge between two items, between two nodes. So given the nodes, the communities that exist, and whether they're members of these communities, and what is the probability that they will connect if they're a member of a particular community. We're going to take the product of all the communities that they're likely to be members of, and tell whether they should become friends or not, whether they're going to meet them together. So if we should place an edge between the two nodes. Now, if they belong to multiple communities at the same time, of course, their likelihood to become friends increases. And again, we're taking 1 minus the communities that are not belong to. So the more communities they belong to, their likelihood to connect increases. Because you see here, these the red ones are more densely connected with each other. So, given so the idea here is, given the set of nodes, the communities, and whether they're members of the communities, and the probabilities that they will become friends if they're a member of a particular community. So if we have all these 4 pieces of information, we can use that to create a model that from this information will allow us to provide the structure of the network. So which node links with which node, and what are the communities and how do they overlap. So obviously the red ones are part of all the communities, because all of them overlap there. So given the set of nodes, the set of communities, whether the membership to those communities, and some parameters, what's the probability of connecting them, if they belong to the same community, we can create a model that allows us to generate the network. So the red ones are very well connected because they have lots of edges, and these ones, for example, are not so well connected. So this is called the affiliation graph model. So set of nodes or vertices, set of communities, the community affiliation, the community affiliation, which community do they belong to. And parameters, probabilities, for each community. We can generate the network. So given these parameters, we can generate the network. What kind of network structures we can have in terms of thinking about these communities? We have seen so far two models. The one model was where we have non-overlapping clusters, and that is the first one, is non-overlapping clusters or communities that do not overlap with each other in this case. So we have community A and all the nodes that belong to that community, community B, and the nodes that belong to that community, and there's no overlap. It is possible that they can overlap. So the orange nodes belong to both of these. So if they're not overlapping, there is lots of edges in between them. The nodes inside of the same cluster. So we have a densely connected nodes, but still few, according to our affiliation graph model, still few edges will be created to the other communities. If they are overlapping, then this is the overlap here. So the orange nodes are the ones that overlap. Or it could be the case that they are completely nested with each other, the way that you have seen with the hierarchical clustering. And so the way to model this overlap is just to show that there are edges here. So the orange nodes have edges to both community A and community B. How are we going to model the nested ones? Very similar to the overlapping ones. So there is a big parent community that contains both A and C, even though A and C are not linked with overlapping with each other. So we have a big parent or mother community B, and a small community here that has edges to B, and a small community C that has edges to B. And as a matter of fact, the difference you see here from this one is that all of the nodes of A have edges to the mother community, which means that it is completely inside it. Over here, not all of them, but just some of them have edges to the other community. And so, what we have shown is we have a model that's going to generate the network. Can we do the opposite then? Given the network, what to find a model that describes this network. So turn around. Given the network, we want to find a model that would generate this network property.